Hi, it's Alex Grobel, and this is my oral part of my final exam. So we're going to first start off with discussing in detail the connections between differential and integral calculus. So differential calculus is a study of how a functions change as its inputs change. A differential equation is an equation for an unknown function that involves the derivative of an unknown function. So what you kind of like when you're using it to find like a derivative. So like we use it a lot in like physics-based like questions, and it's really good for like modeling different factors of what's going on to find something. Whereas like your integral calculus is kind of like it's the exact opposite of your um derivative kind of. It's your antiderivative. The This comes in handy when you're dealing with like constants, and because we know the derivative of a constant is always zero, and when you're using an antiderivative, you're moving backwards of your derivative to find that constant. So that's like your C value. So you're using your derivative of your differential equation, but you're moving backwards to find your integral of it. So it's kind of how they're related, is they're kind of the exact same, not function, but like family, and you need one to find the other, but you can find one without the other. They're both, for every derivative there's always an antiderivative, and for every antiderivative there is a derivative, is what I'm trying to say. So I'm going to move on to part 2. Um, so your f of x plus h minus f of x is your it's your dx. It's what you're trying to find. And what dx is your infinite amount of values for x. So like you're trying to find your width of your infinite amount of values. And you need your dx to find your derivative. So what that first part of that equation is saying, it's kind of just in simpler terms of trying to find your h value, because it's just saying x minus x. So you're just trying to find your dx, a part of your derivative, which is dx over dy, which is your derivative. So you're just trying to find your dx, which is your part of your slope. So what the next part is your f of x plus h minus f of x over h. This is your difference quotients, which is another way to get your derivative of f of x. And it is your instantaneous change of f of x at one point of tangency. So when you're like looking at a slope line, it's your one point of tangency of that line. For your limit of that, as x approaches, or as h approaches 0, this is a limit definition of the derivative, which represents the slope of the line. Any number of given x, which is the limit of which the limit exists, we regard as f prime as a function of x, and this is just your derivative. So this is just your limit. You're using this as to find your derivative. So something that I'm more confident on, which is the chain rule. It's probably my favorite rule out of all of them. And we're talking about, is it in the most important or not as important as we like say it is to be? I think it is very important. I think it's actually the most important. This rule is a rule, so it kind of fitting for its name. It's the chain rule, because we take its derivative, we use it to take derivatives of composite functions by chaining them together. It can be thought of as taking the derivative of the outer function and applying it to the inner function and then multiplying it by the inner function. it kind of like breaks up some of your harder equations. So this is a weird way of how to like think of the chain rule, because this is how I learned it myself, because I was having a really hard time originally with how to, I kept on wanting to add things or flip them. So what I did is, so you have your small f prime times your inner function times the derivative of your inner function. So what I did it as, I kind of broke them up into like different personality groups, as so like your f prime, which is your outside function, always needs a buddy to go with him. So that's why, so you take your derivative of your f prime because he's the one that needs to change, but he always needs his friend to go to like the bathroom with him, so that is your inside function. But your inside function is very confident, and he can always be by himself, so he can change by himself. So you can times it by the derivative of your inside function. So the chain rule is f prime of g of x times g prime of x. So you can also use this to like break up harder equations to make it easier on yourself. So part 4, which is discussing change of rates problems. So first off, I would draw a picture of what's going on. Without a picture, you do not know what's going on in your problem. It kind of just like simplifies what you're actually doing, because if you try going into one of these problems without like visualizing what's going on, you don't know what's going on. Like if you had a balloon and it was shrinking, but you didn't actually draw it, you wouldn't understand what was going on. Or when you're doing a sliding ladder problem, you need your drawing, because when you're naming your different components, it's easier to be like, okay, so this is X over here, and this is Y. So always draw out your problem first. Always. Next is to like write out your equation of what you're doing. So if you're trying to find your area of like the area of the surface of the balloon, or to find your angle or your speed of how fast it is, you need to know what those equations are. So write out the equations you need, so like Pythagorean theorem of what's going on. You can also use like similar triangles, your 90, 30, 60 degree triangles. Then you take the derivative to respect of both sides of the equation, and then you solve for whatever you're looking for. These are probably one of the easiest types of problems because they're really quite simple of what you actually need from them. Your next is your optimizing problem, or maximizing or minimizing problems. These ones I'm a little bit more like iffy on. So first, you have to figure out if it's a maximizing or a minimizing problem. Then you write out your formula. Make sure you identify your edges or your constraints of your problem, and then solve for each constraint for one of the variables. And then you just want one of your variables, and then you identify your domain of your problem. So these are just trying to find like your critical numbers of, this is just another way of trying to find critical numbers. And then you just test your critical numbers, and that's how you do a optimizing problem. Thank you.